Interesting interview with Chris Latner, who of course started the LLVM project, about how MLIR really is just a rehashing of APL, and that APL just got so many things right way back then, and they sort of need to be brought forth into these other languages to take better advantage of the hardware. I think that's a pretty interesting point.
Welcome to episode 111 of Arraycast. I'm your host, Conor, and today with us we have a special guest who we will get to introducing in a few minutes, but first we're going to go around and do brief introductions. We'll start with Bob, then go to Adam, and finish with Marshall.
I'm Bob Therriault. I'm a J enthusiast, and I am looking forward to this episode, as I always do.
I'm Adám Brudzewsky. I'm a professional APLer. I'm also looking forward to the episode.
I'm Marshall Lochbaum. I started with Jay and worked at Dialog for a while. More recently, I've been doing BQN and Singular.
And as mentioned before, my name's Conor, host of the Arraycast, and fan of all the array languages, and fan of also future potential ideal array languages, which we will be talking about today. But before we get to that and the introduction of our guest, I think we have a couple of announcements. The first is from Adam, and then we've got one from Bob. So over to you, Adam.
Okay, mine is not huge, but there's this thing called the APL Quest, which has sort of been in bits and pieces until now. It was a series of chat events in the APL Orchard, where we went through all the problems from Dialog's problem-solving competition, so 110 problems. And then follow-up to those chat events where people presented their solutions, I made videos for each one of them. And then there's also this website, APL, you can find it at apl.quest, where you can solve those problems and have your solutions checked, which sort of matches the interface that when this was in an actual competition you could be in. And I've rewritten that site, the APL Quest site, so that it's nicer now, and it now has the video walkthroughs and links to solutions and the chat transcripts and so on in one place. So it's not really a new thing. Everything was available before. It's just nicer now. You can check it out.
Awesome. Links in the show notes. And over to Bob.
My announcement is actually past guest Alex Unterreiner had been talking about KDB and using K. And this last week, KX came out and said that KDB-X is the next evolution of time series databases. They're giving you 16 gigabytes of RAM, 4 secondary threads per process, 8 IPC connections. Best of all, you can run it on premises as in the cloud. This is for personal and commercial use. And also PIX is included as well. So if you were thinking of trying out Q and KDB, this is an excellent opportunity to do that. We will endeavor to get somebody from KX on in the next couple of episodes to talk specifically about this, so that I don't feel like I'm shilling quite as much for them. But I'm very impressed that they're actually doing this, because the last time we had a ShowCon, he was talking about opening it up to more people. And this is definitely opening it up to more people.
All right. Yeah, we will definitely make sure that we've got someone, if not in the next couple, definitely in the next few from KX, if they're willing to come and talk about this more, because that is a very exciting development. With that, it is my pleasure to introduce Asher Mancinelli, whose name may or may not be in the title of this episode, so you might already know that. It is the first time we're having on a coworker of mine. We chat frequently at NVIDIA. We're on different teams, but that doesn't stop us from chatting. He's a compiler engineer on the HPC compiler team, and he's been working at NVIDIA for the last 3 years. Before that, he was at one of the national labs, Pacific Northwest, if I'm not mistaken. So was doing compiler stuff, HPC stuff, before he got to NVIDIA. And we're having him on today. We have a tab in a Google Sheet of potential future guests. And Asher's name has been on this for years, actually. I think very from the genesis of when that spreadsheet or Google Sheet started, because on top of having recently written a blog post called My Ideal Array Language, which I think is going to be the focus of most of this conversation, he also has a YouTube channel that he posts to sporadically, and back in the day had several BQN-related videos I think one of them, very interestingly, for at least the both of us, was related to GPU computation and getting BQN to run on the GPU. So we will link to the YouTube channel. We'll link to the blog post. And maybe we'll talk about both before we get to the blog post, if he wants to share sort of his exploration of array languages. But before we do that, maybe we'll throw it over to you, Asher, and take us back to however far back you want to go, your first computer, your introduction into programming languages, compiler engineering, and take us through the journey of how you got to working on compiler engineering, but also your interest in array languages.
Yeah, well, thanks. I'm so excited to be here. It really takes me back, especially a couple episodes ago when, Marshall, you were talking about, what was it, the 5th year anniversary of starting the BQN project or something to that effect. And it took me back to, well, I think BQN was about less than a year or about a year old when I first started playing with it, when I was still an HPC engineer at the Pacific Northwest National Labs. And I just started playing with the language and really fell in love with it. And every host on this show I have some sort of connection with that I was thinking about as we were starting up. I mean, Bob, I think, welcomed me when I first made my YouTube channel and posted something to the Array Languages Discord. And Marshall took a million of my questions on the BQN channel. And Adám, I think we had a video call where you were explaining some things about APL on IBM 360, the old emulator. And of course, Conor made a response video to one of my YouTube videos, which is when we first talked. And then now we're coworkers and talk all the time about array languages. So I'm just thrilled to be here and nerd out about array language stuff. But yeah, I started getting interested when I was still doing HPC application development, primarily making scientific codes run on big GPUs that we had at the lab. And I started getting interested in array languages and compilers at about the same time. And then from there, compilers and programming languages, and in particular, array languages, have just become a real fascination for me. I think it'll probably be a lifelong obsession or fascination. So I'm super excited to be here and nerd out with you.
So was BQN the first array language that you stumbled across? You said you found out about it around the 1-year birthday of BQN, but had you heard of JAPL and friends before that, or was this your foray into the paradigm?
No, I think it was my foray, unless you want to count Fortran, which we can get into. But yeah, I think BQN was probably my first one. Yeah.
And so that was just from something on one of the Orange websites or YouTube or something?
I don't really remember. Did you may have made a BQN video before me? Maybe that's where I found it, or I don't quite remember.
We'll have to check the YouTube channels for the timestamps. I do not recall either.
I did have a coworker when I worked at the lab. He was sort of 10 years into his soft retirement, where he would just come in all the time and work with junior engineers to sort of train them up. And he worked on old IBM mainframes, writing Fortran as punch card applications. So he was familiar with APL from back in the day, and I don't remember how exactly it started. But
can I just ask a quick question? Because I think people, HPC, high performance computing, that's not something people just walk off the street and start up. So what was your background before you got into HPC?
Well, so I thought I wanted to be an engineer in college, and then I did an internship with Micron over in the DC area. And it was in finance, because it was the only place where I could find an internship, after my freshman year and have any experience. But I started writing little bits of software here and there, and sort of switched halfway through the internship to the software team and got more interested in it. And then that fall of my sophomore year, when I came back, I switched into software. So it's a little bit behind. But after that, so the city where I grew up in is actually the laboratory system is about the main thing that it has going for it. So if you're from where I grew up, which is the Eastern Washington, Tri-Cities area, Washington State, a huge portion of the people that are going to engineering, and they go work out at the site, either at the nuclear power plants, the water treatment plants, or the research laboratories. So it was sort of in the milieu of education, and everyone wanted their kids to grow up and be an engineer out at the site. So that's sort of how I got started. Of course, I had a bunch of friends that worked there and everything, and it was a very generous internship program. So you would be surprised at how easy it is to walk up and get an internship, and they'll train you up if you have the interest and, sort of drive to figure things out on your own. But yeah, it's a really cool space, a lot of really big, really cool machines. There's a lot of legacy. The National Laboratories brought a lot of really important IP to the United States, and developed a lot of key technology. So super fun environment to be a part of. Yeah.
At the point in time when you started getting interested in array languages, what was your programming language? You mentioned Fortran, but like, what was your, was it just, I assume it wasn't just Fortran. You had dabbled in a number of different programming languages. And the follow-up question to that is, what was it about, BQN that made you so interested? Because a lot of people bounce off of these languages, right?
Well, my main language has always been C++, and I've just had little forays into Fortran even, so I wouldn't call myself a Fortran expert by any stretch. But in trying to port these applications to GPUs, I mean, that is what made me interested in array programming because, for folks that aren't aware, in C++, one of the main ways that people offload their applications onto GPUs is they use these libraries like Cocos or Thrust or these various libraries where you've got this descriptor of an array that can be moved over to the, device called the device. Most of the time, device just means GPU. But, you move all this memory over the GPU, and then you have some kernel, which is dispatched somehow to run on this acceleration device. And if you've ever used it, it's pretty painful. It's not a super enjoyable experience. But coming to BQN and array languages and seeing how arrays really are the fundamental data structure, the fundamental way to express ideas, and not something that you have to sort of torture the language into accepting, especially something like rank polymorphism, which, to get that in C++ is, you can get it, but you definitely pay a cost to get there. I just had a real appreciation for how elegant and straightforward it was to express things once you started to think in terms of arrays. So that's what really drew me to it in the first place.
Interesting. So C++, Fortran, you see BQN, and you see a potential paradigm that is going to simplify the painfulness that you're going through, maybe not on a day-to-day basis, but as a part of your work.
Yeah, and a lot of it's the same ideas, but of course, in C++, when there's all these extra ideas sort of polluting your brain space when you're trying to think about, a lot of these applications I was working on, we would have this huge code base written in Fortran, and we would be trying to rewrite select chunks of it in C++ using one of these portability libraries to run it on the GPU. And so interacting with both of those, I could sort of see the ways that Fortran was really nice and some really elegant things about the language, and the pain of trying to re-express that idea and all this cognitive load that you have to have in order to think about managing these data structures that in BQN or in Fortran are sort of packaged up as an array descriptor for you. And all that array polymorphism stuff that you don't really have to think about. It sort of becomes second nature when you're reading over everything. A lot of that does have to be pretty explicit in C++. It's sort of, not only is it a little bit painful, it's a little bit harder to play with ideas, and the feedback loop gets to be really, really long. And I feel like the best way to learn is if you combine curiosity with a really tight feedback loop. So as excited as you can be about, porting this Fortran climate application to run on a GPU in C++, that feedback loop really slows you down. And I know it's really hard to keep progressive, but if you can sort of prototype out algorithms in this other more elegant interpreted, but also very polymorphic and also terse, we can talk about syntax a little bit later, but it's terse. Once you get familiar with the ways of expressing ideas, you can just really quickly iterate on ideas before taking it back to the heavier weight acceleration, stuff in C++.
Yeah, I can 1000% agree. It's one of the arguments I think I made in a talk I gave a long time ago. What was it called? Algorithms as a tool of thought, which was a spin-off of the notation as a tool of thought. And it was like a 30-minute talk, but like the whole point of the talk was just that, like, here's 8 solutions to a simple problem, and I can show you all 8, like, comprehensively. Like, they're all 3 or 4 characters, so it's not like I have to like burn through this. It's 8 different solutions to the same problem. And then I think I actually showed 11 at the end of the day that other folks contributed. And part of my point is, like, you can't do this in C++. You can't do this in so many languages, right? Like, there's so much ceremony and noise to try different things out that honestly in C++, once you get it compiling, like, you want to make sure it runs correctly and runs decently, but you might tweak if you want to get performance, but you're not going to go and spend another week trying to get some alternative solution necessarily working. All right. So you've explained your path to the array languages. Fast forward a couple years, and now you've written this blog post, My Ideal Array Language. So maybe if you want to comment on what inspired you to write this post, and then you can, I guess we can talk about it. You can walk us through kind of your thoughts on your ideal array language, and then we can chat about a potential future where this language exists. Maybe.
Well, I'll back up just one more step before we go to the blog post. And that's sort of how I got into compilers, which is when I was still working at the laboratory, I started to get more and more interested in, the stuff underpinning the languages that I was working on. And so I started looking at compiler technologies and, standards and all these other things. And so I started looking into the LLVM project, and I noticed this interesting sub project of LLVM, which is called Flang, which is the Fortran compiler. I thought it was really interesting that we had this Fortran compiler built on LLVM, and felt like nobody really was talking about it or knew about it. It wasn't super widely used, especially at the time. And so I just tried to go through the Git history and Git blame and find people whose names kept showing up in interesting parts of the compiler. And so then I just ended up messaging one of them on LinkedIn, this engineer that still works for ARM. And he was really kind, and we ended up talking. I just asked him, hey, can I write some tests for you? Or can I do any sort of menial work to just sort of get started on this interesting compiler project? And he said, yeah. We met like once a week for a while, and he would teach me about compiler stuff, and I would just write tests for him, do little smaller side projects. And that led me to apply for this job here in NVIDIA, where I work on compilers, part of the HPC team. And so the blog post was very much coming at it from the perspective of a compilers person and not as much an end user, which, there's one section of the blog post where I bring up syntax just to say that I don't want to think about syntax as much, because I think what's really interesting to me is the programming model and the semantics that the array languages give you. And I'm not very good at thinking about syntax. So I sort of wanted to punt on that and say, well, let's think about what we can do to provide a language that really amends itself to being optimized, being offloaded, and running on the really diverse set of hardware that's here today, and is getting weirder and more heterogeneous the longer we go on. So that's sort of where I'm coming from in writing this blog post.
So I just noticed you've added a section at the end, because I pinged you about the paper that trolls Henriksen, author of Futhark, or is author correct? He's the father of Futhark, and we've had him on Arraycast. He posted on Mastodon a preprint archive paper called Comparing Parallel Function Array Languages, and it's quite interesting. I think it's APL, co-defunds, Dace, which I actually hadn't heard of, or if I had heard of it, I had forgotten about it, Futhark, and then, am I forgetting? There might be one more. I think there was 5. Anyways, it compares these across, I think, 3 or 4 different problems. And I haven't read this section of the blog. So I skipped down to the syntax part and then was like, oh, wait, there's a new section in this blog post. So I'm woefully unprepared now because I haven't read that. But anyways, we'll put that on the queue and talk about that later. But yeah, back to, so you've talked about the motivation for this. And so, yeah, what are your thoughts on an ideal array language as a compiler engineer?
Yeah, well, I guess I do want to preface saying, I can give you 20 or 30 other people that I work with directly that would be more equipped to talk about any particular sub-conversation here. So I don't want to sell myself as an expert on Fortran or even necessarily compiler optimization. But when I think about the types of things that have made it easier or harder to optimize Fortran code or C code or C++ code, and the ways that array languages provide that to you and how best to expose that to an optimizer, I think there were a couple key things. I think I listed them in the blog post. One is, I think at the very beginning, things should be unbufferized, and we can talk about that. And rank polymorphism was definitely up there. I might need to pull it up to see what my top list was, but I guess we can start with the bufferizing part of that. Or do we think folks will be familiar with sort of what that means in terms of compiler optimizations?
No, I think you should.
We can
explain.
We can assume that many folks will not be familiar. Okay. So go ahead and give us an explanation.
I will ask the question, if you like. What is unbufferized?
One of the really nice things about Fortran, and one of the things I think people miss about why you can get really performant code out of Fortran, is that when you use an array, by default, you are not just getting a handle to a slice of memory. So in C or C++, if you just like Alex of memory and you've got this array, you've really just got, an address, and maybe you remember the offset, but maybe you don't even remember that. So it is very bare bones what you get. But in Fortran, you have this concept of an array descriptor or dope vector. So what this means, and this is as it's exposed to C code, but the compiler can sometimes get rid of this stuff out from underneath you if you don't use it. But conceptually, an array is actually a structure, and it contains information like the buffer and the length, which maybe you have in C or C++, but it's also got things like the shape and rank. And, in Fortran, you can have like different strides, and the dimensions and the indices can start at different ranges. So you can say this array starts at -3 and goes to +3. So, you've got all these different interesting things that describe an array. And then if you say pass two of these arrays to a function, the compiler gets to optimize as if it knows that they don't alias each other. So in the end, when it's starting to actually optimize, say if you're performing a SAC speed or something, you're performing some operation on these arrays, it gets to treat them as if it knows that they don't overlap, which of course, if you've written C programs that you want to get really performant, you'll know that you need to put, some sort of __ restrict on those pointers to convince the compiler that, hey, these actually don't overlap, and you can optimize with that information in mind, which is really, really important for, say, vectorization, unrolling, all kinds of optimizations. And that idea, I think, is really, really nice. And another thing about it is that if you set up a bunch of these arrays, and then in the end, the compiler figures out that you don't actually need all of that backing memory to get the result that you requested, as you described in the code, then it can get rid of those out from underneath you. While, of course, in C, if you just malloc a bunch of memory, the compiler's going to more or less do what you said and malloc a bunch of memory for you, whether you needed it or not. And so from a compiler standpoint, most of the time, you translate the code into an abstract syntax tree, and you perform some sort of higher level optimizations on this tree structure that represents the program. And then you do some earlier code generation phase. We can take Clang, the LLVM C and C++ compiler as an example. And there's a code generation phase where it then gives you something called LLVM IR, which is intermediate representation, meaning it's another programming language that's only used inside of the compiler, and it's much more restrictive. And then it does a bunch of optimizations on the LLVM IR. And in that case, most things are already converted into full buffers. Say if you malloc some memory, the compiler will turn it into a malloc call there in the LLVM IR, and it'll persist throughout the program. But in the Flang compiler, which I'll just talk specifically about that, maybe we can generalize to Fortran, it's not so. In the highest level intermediate representation, there's a lot of really high level information. So, you've got some AST level optimizations you can perform, but then it's lowered to a really rich, high level representation of the language. It's almost as if you had a more restricted version of Fortran that you could round trip. You could go into this intermediate textual representation, you could look at a file, and then back into the in-memory representation, you could round trip, but it still represented a huge swath of the semantics, including arrays, which may or may not have backing memory in this higher level. And then all the optimizations can take advantage of that. And then eventually it progressively lowers into something that, in the end, you still get LLVM IR, and the LLVM optimizer still gets to run on it. But you got this huge chance in between AST stuff and intermediate representation stuff, or the usual intermediate representation, where you've got a lot of really rich, high level information in the IR that you get to optimize based on. And so in this case, you may have a matrix multiply, for example, and you declare, 3 arrays, and you multiply them together and get a third. Well, the optimizer may look at that and see that you really only need one of those arrays worth of backing memory to get the matrix result. I'm just making something up right now. But the point is that the buffers are not determined in the source code or very early on. And it's sort of opaque to the user how much memory will actually be consumed. And then the optimizer gets a chance to take a crack at removing some of that memory for you. And it gets a lot of high-level information about aliasing, or more importantly, what doesn't alias. And I just think that's really neat. It's pretty critical to my ideal array language.
Yeah, we made a pretty similar point when talking about SAC, that the source code has all this high-level information, and it's really in a format that's pretty great for optimizing. I mean, once you compile the syntax out and get it in a more machine-like format, but with the same semantics.
Mm-hmm.
So yeah, keeping that around as long as possible gives you a lot more possibilities for kind of having the compiler do operations do optimizations that depend on it understanding what the operations actually do.
Exactly.
And on a previous episode, I think the most recent episode, we were talking about replicate. There was an awful lot of talk about the costs of moving memory around. And I think you touched on it. This information would allow you to in place a lot of things when it becomes apparent that they can be done.
Mm-hmm. And one other interesting attribute about these intermediate representations is that they use something called SSA format, which means static single assignment. So at the highest level...
Yeah, well, that's the SA in SAC SAC is...
Oh, single assignment C?
Single assignment C is what it stands for.
Yeah, well, there you go. Well, yeah, once you've converted something into static single assignment form, it is almost as if you've coerced your source language into being purely functional. It's not quite, because you still have memory references that are SSA values that you store to and read from. So it's not quite like that. But at least in the case of Flang, it is a little bit like we took Fortran and we've sort of forced it as best as we can into being a, purely functional language that we get to work on. And then once you get past the AST level stuff, you just have this pretty functional, pretty high level abstract programming language that you get to optimize around. And we talk about how that exactly works, but it's really pretty astounding, some of the high level stuff that is in the highest level intermediate representation. And I think that's pretty uncommon. I think usually you've got that high level information at the AST level, but rarely do you have that high of level information while also having it in an SSA format. I think it's pretty unique.
I guess a follow-up question is, what is it about Fortran that enables this? Like, obviously in C++, it's just absolute anarchy. You've got references, you've got pointers, you've got, in the worst case, reinterpret casts. So like, you can imagine why you can't, know this stuff and make these kinds of optimizations in a language like C++. But are there things specifically about the Fortran language that enable this kind of language feature, or I guess compiler, optimization?
Oh, it's definitely a language feature, yeah. And again, I'm not a Fortran expert, but the semantics as prescribed by the language when it comes to arrays are really friendly and amenable to optimization. I mean, a user can ask like, hey, I actually really want this array to be a pointer to this other thing so I can control the memory. You can ask for all that. But by default, it's as if you had a rank polymorphic structure and wrapper around your memory that the compiler had all sorts of information about. So, for example, when I worked at the laboratory, there was this numerical code that I worked on where all the matrices were represented by these structures that had all these member functions that knew how to do all sorts of stuff with the data. And when you wanted to get a handle to the data, if it was a 2D matrix, you would have one linear buffer, and then you would have a secondary buffer that was, an array of pointers to pointers, so that you could do the nice little open bracket I, close bracket, open bracket J, close bracket, that sort of thing. And then it would scan over and set all the pointers to be, offsets inside of this linear memory, so that you could have, something like indexing into a matrix, but it would really keep using linear memory. So it was more amenable to vectorization and, capsulites and all that stuff. But all that stuff is sort of given to you for free by the language, because it describes arrays as this sort of descriptor around memory that tells the compiler and the users a whole bunch of information about shape and, step length and all these things. So definitely a language thing, and something that compilers could take quite a bit of advantage of.
So did you ever get around to explaining why you call this unbufferized?
I'm sorry. Maybe I lost it. The key concept is that the description of like, at this point in the program, I want to malloc this much memory is not there in the highest level IR. So you've just got a conceptual array that you perform operations on. And once it's been lowered enough and optimized enough, then the compiler will say, okay, we actually need to set aside some memory here and here. And if you look at, how these machine learning compilers work, it's all very much the same way. At the higher level, you do something, I think it's called return passing style, I think. It's something like that, where if you perform some operation on a tensor, I guess in machine learning land.
Continuation passing, maybe?
No.
Is that a different thing?
Yeah, there's
Okay.
There's this other duality between passing in the destination as the first argument, or just returning a brand new thing.
Oh, there's a return oriented. No, that's the exploit stuff. I don't know.
Well, in machine learning land, if you want to say change something about a tensor, it's pretty common that you'll have this insert operation that just returns a brand new tensor. And so all subsequent operations use that returner thing. And so sort of like anytime you modify it, you just have a brand new tensor that you operate on. And then there's some optimization paths that will go through and figure out how much memory is actually required, how much can we fuse together, how much do we actually need here. And that's sort of the style of the higher level Fortran intermediate representation in cases where it's possible. So you don't actually see, if you just look at the code and read it as a programming language, you would think that there's memory all over the place used for free, and you can just keep allocating all over the place. And then the compiler will then figure out where the memory is actually needed. And then you would have memory references that are passed around and you store into them or read from them and that sort of thing. But the idea is that the backing memory for things is not present in the IR at the higher level. So you can do all sorts of analysis and you're not worried about, the pointer to the memory escaping or anything like that, because you're operating at this higher level. And then as you progress through the compiler, it becomes more concrete and you actually have a malloc or a stack allocation or something like that.
And I'll jump in here, not totally related, but I can compare to APL because Bob brought up replicate too. So an interesting thing about APL, as there is no compiler, the compiler does not make these decisions about where the memory goes. And something that can happen with replicate is like if you look at our BQN performance graph for replicate, I have a graph relative to the density of the left argument. So as the density goes up, generally it gets slower and slower because the result is larger. But once you get to full density, every value is a 1. What happens is it does the sum to figure out how long the result should be. And then it sees that, oh, the result is the same as the argument. And then it doesn't allocate any memory. It just returns it makes a reference to the argument. So, of course, you have this big cost in doing all the allocations dynamically that then if it were compiled away, you would just do one big allocation at the beginning probably. And then all the different code would know which section of the allocation it gets all in advance. So in APL and BQN, you have every time you make an array, you have to call the allocator and say, hey, give me some more memory, and it'll give you a pointer and all. But you have the great advantage that you can choose at any point. You have the most information possible when you allocate that. If it turns out you don't need the memory, then you don't need the memory.
Yeah, a lot of trade-offs between fully offline compiled or online compilation or interpretation, a lot of steps in between with a lot of interesting trade-offs.
Has Fortran always had that ability? Is it something that existed from the early? I mean, when I was studying computing science, and I'm an old, Fortran was old. It predates me. It's 1953. So is it something that's always been there and just wasn't taken advantage of, or was it added and there's been numerous versions of Fortran?
You're testing the limits of my Fortran knowledge, but what I can say is that at the very least, whether it was allowed by the language or not, compilers have changed a lot, which have allowed this to happen. So compilers used to be streaming, and they cared a lot more about locality in a way that most people don't think about locality today. So if you've ever used the TCC compiler, I'm fairly certain that TCC is a streaming C compiler, in that you've basically got a stream of tokens coming in that's your source code. And as it scans along, it's spitting out assembly the whole way. It's not really stopping to think about the whole program or as much of the program as it can see and optimize it. So I don't really know what the older Fortran compilers were doing. But if I had to hazard a guess, I would say it's that they were very concerned with doing some local analyses, maybe within a few statements, but memory was so much more expensive relative to other operations at the time that you really couldn't hold much more than maybe a function, maybe parts of a function if it was really big in your compiler at a time. So this sort of larger analysis of what buffers are needed when, where, I don't think is really possible until more recent innovations in hardware and software that, let us make these bigger, more powerful, maybe memory or compute intensive and, sometimes slower compilers that can make a lot more clever decisions about what happens in your actual program. But I think the semantics of the arrays are pretty consistent. I don't actually know.
Well, I wonder if what's been added is actually more facilities for passing arrays around. Like I would expect in early Fortran, if you could pass arrays to a function at all, it would be like passed by the name and then the function. So pass by reference, but not a reference to the array, a reference to the local name. And so you could even change the, well, probably in Fortran you couldn't change the type, so you couldn't do much. But I would think that the ways that you could pass arrays around were very limited. So when C came, it was probably seen as more featureful than Fortran because you can just pass pointers anywhere. But then when you get to trying to optimize it, that turns out to be a pretty big weakness.
Yeah. And in terms of parameter passing, there's all kinds of interesting things too. So you bring up a good point. For example, if you have a function that takes like a one-dimensional array, a flat array, but you pass in something that's, I don't know, 6-dimensional. Well, if the compiler can do enough analysis about the function and this array before it gets passed in, it can do something called repacking, or it will, actually repackage that array into a different array before passing it in, depending on the stride and offset information in the original array. It might be more beneficial to create a whole new thing, pack it in, call the function, and then copy it back out. So it's a lot of room for optimization. I don't quite know which language versions, like 77 or 90 or 08.
Yeah, I mean, that's got to be a newer feature.
Yeah, I couldn't play it.
So it's interesting. The early Fortran was just so limited because that's all they could think of to do. But over time, it turned out that they had the right limits, which allowed them to add new functionality that's the good functionality instead of all this bad pointer aliasing functionality.
I would agree with that. Yeah.
So if you were to start now with the ideal foundational language to put a compiler together, it sounds to me like Fortran's actually a pretty good choice.
There are some parts of Fortran that I would definitely love to take forward, and there are also some that I would not. Yeah, there's a lot of really cool stuff, though. I mean, I love talking about the where feature in Fortran just because I find it so interesting. And this is one of the features that's represented really well in the high level intermediate representation. So you can do something like where A, B equals C, and that's interpreting A as a Boolean mask that applies to all of B and C. And so it'll perform that assignment only where that mask is true. Does that make sense?
Yes.
So you can do sort of where, do this, elsewhere, do this. And it's just sort of this really, I mean, I just sort of love that description. I mean, just reading through that, okay, where this mask holds true, then perform this code, otherwise perform this code. And then it will, perform everything for you. And I just love the readability of that. And if you look at the intermediate representation, which is to say that the textual format that the compiler is optimizing internally, it keeps around this sort of rich information in a way that's easier to optimize. And I just think that's a really wonderful idea.
Yeah, so that's a lot like add in APL, except where add has an operand function, you just write, what you do on that portion of the array, which is not any sort of first class thing at all, I assume.
Yeah, and it comes up frequently on ADSP when Bryce and I are chatting that it's like the equivalent of the thrust stenciled copyif, where, and also too, it's morally similar to the SUMIF, I guess, in Excel, where you can basically give it multiple ranges and say, I want you to do something on this range based on this other range, which honestly, it's a very frequent, it's a very common real life thing you want to do. There's no real name for this kind of operation though. Like it's named something different in every language / application. Because I guess, you could argue that Excel is a language, but anyways, we'll table that argument for another day.
I think maybe a masked operation is what I'd go for, trying to explain it to people who don't necessarily know anything in particular. That's what it's called for vector instructions that have masking.
But it's more than just a mask, right? Because you could, if you give it indices, it's not a mask, and it can be out of order.
Well, can you give it indices?
I think you can, and I think you can put sort of arbitrary behavior inside of those where statements. This is really testing what I know, but
I mean, so if you give it indices, it's kind of more like a for loop.
Yeah, sort of a for loop, and then you've got an if else inside of there based on them.
You have to wonder what happens if you pass the same index twice.
I want to know.
So does the compiler.
That's important.
Yeah. There's this really interesting document that one of my colleagues put together. I don't know if he wants to be named, so I won't name him, but he's pretty into functional programming and everything. And in the document, one of the ways that he prescribed that arrays would be conceptualized inside the compiler, or a way that you can conceptualize arrays when they don't have a backing buffer, is just a function that maps indices to values. And if you think about arrays like that inside the compiler, and then later on in the compiler, you realize that you do have to commit some of those values into memory somewhere, but it's just not assumed that they need to be in memory. It's, just a constraint of the compiler that eventually some things will need to be in memory. But I just love that conceptualization of arrays as a first-class citizen, and it's just a function that gives you values based on indices, and that's really all that you can expect from the compiler unless you ask for other stuff.
Yeah, well, so then if you map a function over the array, that's like composing two functions. And if you view it that way, you automatically get loop fusion.
Absolutely.
Speaking of loop fusion, the keyword there being fusion, I'll ask one final question, unless if others have questions before we maybe move on to another of the bullet points, because we've technically just been on tangents off of the first unbufferized bullet point. In my mental model, I was thinking that the unbufferized language feature is not dissimilar from JAX's like JIT compilation and function tracing, which for the listener that's unfamiliar, JAX is a repo or project out of Google. It's built on top of XLA, which I think stands for Accelerated Linear Algebra. And that uses IR that's called, I think it was called HLO at first. Now it's called stable HLO, which H and L stand for high level optimization. And when you are JITting a function in JAX, it'll do some function tracing with the goal of ultimately, if you're targeting a GPU, like reducing the number of kernels you launch. So if you don't JIT anything, you're just going to get a kernel launch for every single operation in your function. But if you JIT it and it uses this HLO to do a certain number of optimizations, you can reduce the number of kernels like drastically, which in other words is like basically preventing materialization of some operations. And when you think unmaterialized, like I think there's kind of some like loose equivalence to unbufferized.
Yeah.
How like dissimilar or similar is my mental model to the Fortran unbufferized language feature?
No, I think that's right. Well, so most or all of the machine learning or AI compilers use this technology called MLIR. And Fortran was one of the very first users of MLIR for any sort of general purpose computing. I think the majority of uses of MLIR are for little Python libraries or domain-specific languages that then turn themselves into MLIR, which then gets optimized. So might be a good time to talk about MLIR more generally. And I don't know anything about the HLO dialects of MLIR, which is typically what they're called, but they usually fall into one of two categories when it comes to arrays or memory references. And that is a tensor or tensor-like dialect and a memref or memory reference like dialect, and the former of those being the unmaterialized version and the latter being materialized. So if you look at something that uses, there is actually a tensor dialect in MLIR and also a memref dialect. And then there's a bunch of other ones that do very similar things. So I'll just talk about those two general ones as they're sort of shared by everybody in the LVM code base, and then other folks have their own dialects. But the tensor dialect is the one that, for you to insert an element, for example, there's an insert element operation you can perform on a tensor, and you pass it a value or a slice or something you want to stick in there. And then it returns you a brand new thing in, SSA format, like we talked about. And then you use that returned thing. And so you're basically never modifying anything in place. It's sort of disallowed by the intermediate representation language itself. And then as that gets progressively lowered after being optimized, it is turned into a memory reference or memory reference like dialect if it needs to be materialized. And at that point, inserting anything into it, you're just performing store. So you might have a memory reference up at the top that's allocated on the stack or something. And then to do stores, you do actually just store into it, but you keep using that original memory reference thing at the top, because now we've got, an actual reference to materialized memory. Whereas in the tensor dialect or any other dialect that's similar to the tensor dialect, you're using the return value each time, and the memory behind it is not actually material yet, which is more amenable to optimizations. So I don't know anything about HLO, but that's sort of the shape of dialects that these things come in. So maybe it's time for an aside on MLIR, you guys told.
Well, I mean, it is mentioned in your blog post, but technically it's mentioned, I think, in the unbufferized or automatic bufferization section. So But yeah, so what is if automatic bufferization is maybe not number one, but it was the first thing we talked about. What's the second thing in your future ideal array language?
I mean, it's got to be all the really nice rank polymorphic stuff that make array languages so nice to use. I mean, really general algorithms that apply to all different kinds of arrays. You can write things in a really general way. And of course, Fortran has this notion of an elemental function that's sort of agnostic to the array shape kind that it operates on, similar to like a ufunc, I think it's called in NumPy or Numpa. I don't remember, but it's similar things where you describe these sort of general functions or algorithms that can apply to arrays more broadly. And I think arrays really should be the fundamental data structure for things. And the operations around them should be really natural and extensible in such a way that a user is able to write something that is at least as powerful as the compiler is able to provide. So that's something I think the Mojo folks seem to be doing pretty good at, even though a lot of their compiler stuff is still closed source. Seems like they're able to do quite a few compiler-y things in the standard library or language because it's built in a pretty extensible way. So I'm rambling again, but hopefully that gets at your question.
No. That's awesome. Does elemental, my brain translated that to element-wise. Is it the same thing or is it greater than that?
I believe it is just element-wise, yeah.
And does Fortran give you an ability to define functions that operate rank polymorphically? Or is that just a thing that for your future array language that you want?
I believe that it can, and I don't quite remember how to do it in the language, but there's a lot of really clever stuff you can do there. Like I think in our, in our NVIDIA meetings, we've talked about how Fortran has just a little taste of dependent types in it. But there's a lot of other interesting stuff that you can do around, the assumptions that you don't need to make about arrays that you accept as parameters, that sort of thing.
Yeah, we've definitely talked, not just Fortran, but Julia has a little bit of that as well. Although there's very little literature calling or referring to the language features in Julia and Fortran as like quasi-dependent types. Although if you search hard enough, if you ask the LLMs, you can coerce it into telling you that they do have with the right set of questions. All right, so we've got automatic bufferization or unbufferized. We've got extensible rank polymorphism. What else?
I don't know. Hardware is it's getting very strange, and I only see it getting more and more strange. And I feel like this paradigm is just really well equipped for the future of computing more generally. Again, I don't want to portray myself as some sort of expert, but it just really seems like this array polymorphic, really extensible paradigm is really, really future-proof when it comes to the changes that are coming in hardware.
Do you have thoughts on why up until now there has been, I guess, less exploration? There's a couple projects out there. There's CodeFunds, which makes use of the ArrayFire library. Link in the show notes. We've talked to Aaron about that at least once. I mean, we had him on twice, but I think the second episode wasn't necessarily talking about CodeFunds. But there hasn't been a ton. I mean, I guess if you include single assignment C, they have a CUDA backend. But so you're saying it's future proof, but there currently, like present day, there doesn't exist an array language per se, like in the Iversonian sense, that can target all the heterogeneous devices and compute out there. Do you have thoughts on I think both of you and I know, I mean, we chat about this all the time, wish that language existed, but
well, I think it's a function of money. I mean, it does exist in the machine learning world because there's plenty of people have money at stake in order to best utilize these GPUs. I mean, there's specialized hardware now, not just in, the NVIDIA GPUs, but also the upcoming ARM scalable matrix extensions that are just matrix multiply specific hardware. All these tensor cores that we've got that are, all these things that are just meant for matrix multiplication because that's the best yield for, hardware manufacturers to focus their energy right now. And so we've got a million Python domain-specific languages that do sort of convey all these semantics, and they leverage hardware, honestly, pretty well, it seems like. But, I think a lot of programming languages that are in use today aren't necessarily taking the best advantage of multi-core or shared memory or SIMD extensions. So parallel programming is really, really hard. I think we'll need a little bit more time for the rest of the features to sort of percolate to other languages. But I think the paradigms that are set up in these languages makes them amenable, whereas other languages will have a much harder time. I don't know if you saw the recent talk from, I forget his name, but he works on OCaml stuff, and they recently introduced multi-core OCaml, and just the staggering amount of effort that went into getting OCaml really ready to support multi-core stuff. I mean, it's a tremendous amount of work. And I think a lot of languages are there too. I mean, SIMD is really hard to get right. It's really hard to get right, even with a lot of good compilers and people that are writing their code very thoughtfully. I think it'll just take more time.
Well, and I can give some more of the APL perspective on this. In our quote squad group, which is still ongoing, our last paper was titled, Is APL Really Processing Arrays? And what they did was they took a study on, this was in the mainframe days, it was 1979, I think. So the way everyone evaluated their APL was by sending it to the mainframe and to run, and which would give their answers back. So with a centralized thing running, that's actually a really great place to do studies on APL usage. And what they did was to measure all the array allocations across a bunch of different sessions and take the average array size. And they found the average array size was about 30 elements. They reported on two other studies that found average sizes of 14 and 28. So actually, there was a big push around this time to get APL compiling. And the reason wasn't because it was better for working with big arrays, but because it was better for working with small arrays and one element arrays in particular. So from the APL perspective, I mean, really, it's just like multi-core feels to me like a very fringe use case in terms of what APL family array programmers do. Because like I just never have arrays that big. Like who has that much data lying around? And of course, I realize that there are many people doing this, but they don't use APL, and the APLers don't really do all this big data application. So there's kind of this disconnect between the programming language implementers that might be able to implement some multi-core stuff. And I mean, they have started working on it, like J, as we've had Henry Rich on to talk about what they've done in J. But basically, I mean, these implementers haven't been but so incentivized to work on HPC problems because there's just no overlap between the programmers in those communities.
J does make quite a bit of use of SIMD stuff, though, right?
Yeah, and so SIMD is great for small arrays.
Yeah.
So like if you've got a 20 element array, SIMD is already worth it. Oftentimes as small as like 5 elements or 2. So Dialog does a lot of SIMD, J does a lot of SIMD, so does BQN, K does, I'm sure. So all the major languages are trying to use the vector instructions pretty well. Multi-core, I mean, it has obvious solutions, but it's more work to kind of fit into the array paradigm, the interpreted array paradigm. And it's like you have to be able to split your data up into big enough chunks that you're not just spending all the time communicating between processors.
Yeah, or much less put it on the GPU where you need enough data that you need to send it all the way to that, whole other machine and then run some stuff on the GPU before sending it all the way back. I mean,
yeah, and you better hope that nothing you can't do on the GPU happens in the middle.
Yeah.
Fun little anecdote here. I Googled, is APL really processing arrays, which is the title of the paper Marshall mentioned. And of course, I get back from Google now an AI overview, assumably from Gemini, answering, yes, APL is specifically designed for processing arrays. And anyways, the second result is the actual paper, but a bit humorous that the title of the paper from 1979, I think it was, is a question that now the AIs are laughing at, being like, of course, it's in the name.
Yeah, well, I don't think it's the greatest title because it's like, yeah, I mean, even empty arrays are arrays. That's what APL is. Maybe they meant, is it processing real arrays? Of course, that's easy to confuse too. So I don't know what they should have titled their paper, but their title is a bit confusing.
Well, I mean, it brings up a great point. I mean, like, you think about garbage collection strategies. I think that's sort of the premise of like generational garbage collectors, is that most things die pretty young. Meaning, like, you could just sort of collect most stuff pretty soon, and then you can move it on to the older generation if it actually does need to outlive. And you compare that to other workloads where, of course, people are using Python to get honestly relatively good performance for those workloads because, by the time you send everything to the GPU, like you can keep that GPU running more quickly than the Python interpreter limits you, for those workflows. It's not like the Python interpreter slows you down. So pretty workload specific in a way that I think is interesting.
Yeah. And definitely, I can say there are programs where most of the work is concentrated in big arrays, like the BQN compiler. I know is one. It couldn't possibly get the performance it gets if it was working mostly with small arrays. And so for those things like well, all the interpreter time, as well as the garbage collection, really just don't matter. And then it's much more important to do if you are going to compile. The reason would be to lay out the memory, to fuse loops, to reduce memory usage and things like that. It's all about memory bandwidth at that point.
Mm-hmm.
So yeah, different programs have very different requirements.
Yeah. There's this interesting interview with Chris Latner, who of course started the LLVM project and Swift and, all the MLIR, all these other projects, about how MLIR really is just a rehashing of APL, and that APL just got so many things right way back then, and they sort of need to be brought forth into these other languages to take better advantage of the hardware. I think that's a pretty interesting point.
Yeah.
Speaking of Latner, I mean, you brought up Mojo earlier. I'm not sure how many, because has Mojo might have been mentioned like briefly as a throwaway comment once or twice on this episode, but I don't think we have chatted about it at all. Do you have, as someone who's, writing a blog about a future ideal array language, and there's, a bunch of initiatives out there, do you have thoughts on Mojo and what Chris is doing with that? Or have you played around with Mojo at all?
I have a little bit. It seems really nice. It seems extensible in a way that I can really appreciate, meaning that, if the design requirements of the language change, I don't think that it's necessarily going to be that invasive of a change to the compiler or language specification, because so much of it can be done in library land, and you're not relying on these compiler internals like you are in the C++ standard library, for example, to get access to certain features. Yeah, it seems nice. It's hard to say because a lot of the internals I don't think are public yet. I don't think any of the compilers out there yet, but the standard library and a bunch of kernels that they're, claiming particular performance numbers on are out there. But I would really love to see what's going on with compiler to get an idea of, really what's happening in the language.
Yeah, the most recent thing I heard was he was on, Chris Latner, that was on Richard Feldman's podcast, Software Unscripted, for the second time. At first, when I saw the headline come up in my podcast queue, I was like, well, wasn't he just on? And or like, is this like a repeat episode that they had to release again for a correction? But it is actually the second time he was on. And they mentioned, the compiler stuff is still closed, but they did open source, I think it was 500,000 or 600,000 lines of Mojo code that they've been writing. So at least there's more out there for people to look at. But yeah, the internals are still closed off. But I think their roadmap is to open source stuff, but it's just not in the state right now where they want to. And I guess we buried the lead. Mojo, for those that haven't heard, it's a new, I don't know if you want to call it, programming language from Chris Latner, who's worked on Swift and a ton of other things, LLVM, MLIR, and its goal is to be like a superset of Python, and that existing Python libraries are going to work with Mojo, and that over time you can like port your Python code to be Mojo code, and it's going to have extra features. Like I think they have structs right now that is going to enable them to offload stuff to heterogeneous compute, and they have some examples that like super 40,000 times faster, but that's cherry picking on some really bad Python code. So on average, you're probably not going to get a 40,000x increase by switching to Mojo, but it's an interesting, exciting project, and Chris has been successful in the past. So
yeah, super. I mean, very integrated with the MLIR project in a pretty interesting way as well. I think they use very little of the dialects, the available intermediate representations that are available upstream in the MLIR project, to just use everything downstream themselves, which the reasons for those decisions are pretty interesting, I think. I guess just guessing at them, since I don't know, I haven't asked anybody myself, but yeah, pretty interesting project. I'm excited to see for when more people start using it.
And speaking of other projects, maybe this is a good time to bring up the bonus content that you added to the end of your My Ideal Array Language blog. So as mentioned before, there's a preprint of a paper that I think Aaron Shu, Troels Henriksen, and a bunch of other folks are co-authors on. It's like a 75-page paper. Full disclosure, I have not read the whole thing. I skimmed the most of it, went to the results tables. I wish they had to put a couple graphs in there. It would have been nice to see a big, beautiful graph, but it's just tables. But then the end section has a kind of summary of each language. And I think single assignment C was the one that I was forgetting, on top of APL, CoDefunds, DACE, if that's how it's pronounced, and Futhark. Anyways, I'll throw it over to you to share your thoughts because like I said, I haven't read that extra section in the blog, so I'm hearing it first here, live on the pod.
Oh, it's pretty short. Each section, evaluated the different languages on different kernels and everything. So at some point, I started kind of skimming through once I sort of got the point the paper was trying to make, and read through the conclusion and everything. So I haven't read every page either. But my thoughts on it is that it's very interesting. My main interest lies in how amenable these languages are to optimization. And it seemed pretty heavy on discussion of syntax and how ideas are expressed, or what ideas are able to be expressed in one language versus another. And that part's just a little bit less interesting to me. So while I thought it was a really cool paper and is maybe useful for designing the language, like I said at the beginning, the syntax section in the post is sort of intentionally a void, so that we sort of punt to figure out, whenever we figure out what our ideal users are, obviously Chris Latner has decided that his ideal users are primarily Python developers, so the language is trying to be a superset of Python. And since I don't know, this is just my sort of random thoughts, I sort of leave the syntax part a little bit blank. So that's why it was a little bit less interesting to me. I thought it would be really cool if there was another paper or post that looked at the semantics that the languages describe, or were able to describe, really naturally in a way that users might stumble upon themselves by experimentation and iteration loops, and then how amenable those were to being optimized and performance and that sort of thing. I thought that would be really interesting, especially since you can sort of imagine the ideal syntax for a language and the ideal user that's an expert with that language, and there's just no optimizer for it. So you just get out what you put in, and then performance is nothing super special. So sort of, yeah, that was my thoughts on it. I thought it was a really cool paper. I loved reading it, but wasn't squarely in my interest. If that makes sense.
Yeah. I mean, I agree with that sentiment. And I'd love to see this turned into, like, there's the 1 billion row challenge or whatever, where it was some open source thing and someone threw it out there, and then like over a weekend there's hundreds if not thousands of submissions of people trying to tune their language, whether it's Kotlin or some other more esoteric language. It'd be very cool to see this paper kind of expanded on, so it's not just, and I've also just, while you were speaking, remembered that Haskell's Accelerate library is also in there. So I think that's the full list. Maybe I'm missing a seventh, but it would be really cool to see. Like, one of my first thoughts was I would love to see what all the Python, PyTorch and JAX and all these things are like. And maybe that's what DACE was, but I guess I'm less familiar with DACE. So my thought was I would love to see these Python frameworks, how close, because I totally agree that in the paper, they talk about the lines of code compared to the perf. And that's the thing, is I need to take a closer look to see how close the DACE code would actually be to something like JAX or PyTorch. But I think PyTorch and JAX are going to get you not as terse as APL, obviously, and CoDefunds, but it's going to be a lot less verbose than the CUDA baseline or whatever they had. And so ideally, you get pretty close to the tersity of APL and whatnot, but then matching the best-in-class performance, right? That's the dream. Or I guess the dream is actually just to have APL having best-in-class performance when you're targeting a GPU. But in the meantime, it'd be nice to know if the Python libraries can actually get you there. Like you said, we need a follow-up paper or something in order to get those results.
Yeah, I'm pretty sure some of the Python libraries even are more so wrappers around library calls than they are full compilers, because if you can just nicely get in your call to some optimized flash attention thing, then it might not matter. But some of those Python, DSLs are, I guess, more full-fledged compilers that do a lot of clever stuff to get the best perf out of the accelerators.
All right, so we went from tangent to tangent, and we're going to double pop the tangents and come back. Are there any, final things? I mean, I haven't actually checked, but I imagine, oh yes, we are well past the hour mark, as per usual. But that's okay. Are there any other things about, your future ideal array language that we didn't talk about that you want to highlight, or even if it's not in the blog or something else that you were hoping to bring up while you're here?
Man, I don't think so. I'm sad we're at the end. This has been so much fun just chatting about everything. I think there's maybe some interesting conversation around interpreted, versus fully offline compilation.
Yeah, I did have one thing. So you have a note there to check out my talk at dialogue from a few years ago. I also have and I'm putting the link here now, page in BQN that I consider kind of the updated version of the talk that kind of describes what's happening with performance in BQN versus C. And this is specifically C. I mean, it's not comparing to any, more advanced array-based compiler, saying what are the issues with the C-based paradigm, which most people assume is just the best you can do. I mean, I have been criticized for that, the interpretive advantage title, because it sounds like I'm just saying interpreters are better. I took it as a given that compilers have a ton of advantages. And I'm saying, but in fact, there are also advantages for interpreters. And so I described them in that talk. I described them a lot more on that page.
Thanks for letting me know. I'll check that out.
Is this a new, I haven't seen this graphic, this BQNC back and forth. Is this a newer addition to your?
It's several years old.
See,
I would guess 2022.
Okay, so I've just missed this then. I definitely have read all the, not implementation section, but there's another section that has just like random thoughts. I had this all mapped out at one point.
Oh, the commentary.
Commentary, yes. I've definitely read all of those. Yeah.
But this is an implementation.
Yeah, I guess, it's an implementation, so I'm not...
So yeah, the commentary is mostly about the language.
I wish other language authors would have this kind of like blog posts, essentially, or writings of the trade-offs and the motivations behind certain language decisions. Or even if it's just like a random thought about like, oh, people say this about my language, here are my personal thoughts. Because well, Futhark does have a pretty good blog, I'll say. Yes, that is true. Futhark, it's kind of integrated with their website too, so it's very easy to find. But a lot of the, top 50 languages in the world, not as much. You have to wait for a talk or wait for a podcast episode and hope that the interviewer asks the question that you want to know. And half the time they do the political thing where they acknowledge the question and then ask a different question and answer that one, which, is fair enough. They can answer the questions they want. But yes, link in the show notes for this blog post, and also links to the top level implementation and commentary if folks are interested in checking that stuff out. Other final questions from Marshall, Bob, or Adam for Asher while we have him here? I mean, we'll have to have you back.
I would love to.
But while we have you here.
Well, I guess there's always the question about type definition and that sort of thing with array languages, especially J's. You can assign anything to anything else and let the interpreter figure it out. I would imagine it makes sense for compilers. The more you can define a type, the more information the compiler has and the easier it is for do optimization. But it sounds like when you're talking about the unbufferized version, it's grabbing a lot of that anyway. As soon as you start to describe what you want at all, it's going to take that and give you stride information and the ranges and those kind of things, because that's part of the information going in. So in a sense, it's creating its own type. Are there other areas that array languages would benefit from maybe being a little bit more or less dynamically typed?
Yeah, I mean, I think there's a really nice middle ground that you can find in ML languages where, it feels really flexible when you're using the language, but for the compiler, the types are very much concrete. And maybe those concrete types is a union between quite a few different types. So to the user, it's sort of flexible, but for the compiler, it's very concrete and easier to optimize around. So I think that would be really nice. Some sort of ML style, these fancy Hindley-Milner type inference to figure out some type information, but it's still flexible to the user and not throwing type annotations around. I think if it's interpreted and you're not trying to do a whole lot of whole program reasoning, it's only more local reasoning, then I think you can get away with a little more dynamism Because in that case, you only really care about the type in a particular scope. And if you know that, then for all intents and purposes, you know the type because you're just optimizing for that scope. So I don't know. There's a really interesting, I think it's a PLDI talk. I think I linked it in a blog post about how to compose a richer type system for array languages. And just looking at it, I didn't particularly like the ergonomics of it, but I thought it was really interesting to explore, really fine grained, really concrete types for a whole range of, array polymorphic operations. So I don't know. I don't think I've thought about it enough, but I think there's more to explore there.
Awesome. We will link that talk. That was from this year's PLDI, right? The structuring.
I think so.
Yeah. It's linked in the blog post, but we'll get a direct link to it as well. So, all right. Well, thank you so much, Asher, for coming on. This has been a blast. Like I said, we'll have to do this back clearly once you've already created this array language. So you've got n years where n equals the number of years it takes to breathe this into existence. But if the listener has thoughts, questions, comments about Asher's ideal language or about their ideal language and how it juxtaposes against Asher's, you can reach out to us at
contact@arraycast.com. That is how you reach out to us. And I must say, in the last couple of weeks, email messages have kind of dropped off a little bit. So if you were thinking of getting in touch with us, we do respond. We do read them. So don't feel it's talking into a void because it's anything but. But thank you for all the people that have contacted us in the past. We really appreciate it, and your thoughts and questions and everything like that. And continue the good work. That's about it. Thank you, all you contactors from a contactee.
I mean, it is. I've been told that it's the summertime. Via my real estate lookings, and this is a quiet time of the year. People headed out to the cottage where they may or may not have internet, so maybe they're listening to us right now. Well, that doesn't make sense.
They're not listening right now.
Displaced in time.
They're listening at some point. Yeah.
They're listening at the time my voice is played back.
There's something going on with the automatic pilot, Conor, that you get into the glide path here where you're coming into the runway and you drop it off to me and I do the contact thing. And then suddenly the plane veers to the left and is heading off somewhere else. I'm not sure what you're doing with this.
We always land, though. I mean, sometimes it's a bumpy landing, but I think worst case, the wheels fall off and then we skid to a stop. But
what goes up must come down.
Yeah, I don't think we've ever crashed. I mean, I could be wrong. We're all still here.
Any landing you can walk away from is a good landing. Yeah.
Anyways, thank you once again, Asher. This has been a blast, and it's nice, to have a chat that people get to listen to, even though we have chats all the time at work. But with that, we will say happy array programming.
Happy array programming.